Folks, hello and welcome to week 5. We have got a really nice lineup this week as we go through chapters 10 and 11. Chapter 10 is on data mining, and chapter 11 is a section on spreadsheet modeling, which is going to give you some exposure to a variety of different problems that we're going to look at from an Excel standpoint to see what we can make out of those. So I hope this is a good week for everybody. There's 5 problems that I've lined up for this week, given the variety. This is probably going to result in at least 2 videos, maybe 3, but I don't want to rush through these. And the software that I have available to me only allows me to create a 15-minute video. So I probably have at least 2, maybe a third, but I don't want to rush through these. I want to do the best I can to get you started and make sense of these. So let's get going with the first problem out of chapter 10, which deals with a bunch of college data. And what we're going to be doing here, as you've gone through the reading, we'll talk about this idea of Euclidean distance measures, which again is a data mining technique to basically show how two variables, in this case colleges, how well they effectively correlate. I think that's probably a fair word. Based on some inherent data. So there's a number of colleges that we're going to work with here, listed down this left-hand column, and then a variety of different variables related to each one of these colleges. And then, so we'll get over here, and ultimately we will get to this Euclidean distance matrix, but obviously there's some pre-work that has to go along with this. So in the question, what I'm looking for you to do is to relate Cal Berkeley, Caltech, University of North Carolina, Chapel Hill, and then UCLA. And in order to get going here as we approach this Euclidean matrix, distance matrix, the first thing that I wanted to do is I just want to kind of pluck out this data. I did not include the university type. We will just go with the numerical data here. And so the first thing that we're going to do after we pluck this data is obviously we need the average and standard deviation for all of the schools, because we're effectively, let me just go back very quickly. Before we get to this Euclidean distance matrix, we're going to have to normalize Berkeley, Caltech, UNC, and UCLA across all colleges. So the first thing that we're going to do is for all of these quantitative variables, SAT, acceptance rate, so on and so forth, you'll notice at the bottom here, I have already computed the means and the standard deviations of all of those variables. And so again, all I want you to do is to take that and carry it up here. And then what the next step in this, and this is explained fairly well in the book, is we're going to normalize each one of these values for each one of the schools. And if you think back to what we did in the probability section, when we talked about normalizing values in the normal distribution or computing a z-score, that's effectively what's going on here. So let me, ultimately what I want to do is I want to compute the Euclidean distance for Caltech and Berkeley. I'll show you, I've already got it here. I'll show you how that happens. But what I'm going to want you all to do is go through and compute z-scores and fill out the rest of this table. And that way that you will have the data that you need to go through and finish up the Euclidean distance matrix. But again, what is required here is that we're computing a z-score. So effectively, what I'm doing here is I want the z-score for Cal Berkeley's median SAT score. So if you go up here and you look at the equation, I have K17, which is the Berkeley SAT score, minus the mean score K22, which comes from all of the colleges over here on the far left-hand side, and then divided by the standard deviation of all of the colleges on the left-hand side. And so each one of these values that you're computing here will be a z-score using this as your raw data. Sorry about, there's my main accent coming in there. Some of these schools in the northeast got me going here. In fact, Bates, Bowdoin, and Colby are all Maine schools. So I apologize for my Maine twang there. But getting back to this, we're going to compute a z-score for each one of these raw data values. So raw data here, and then effectively what would be the sample mean and the sample standard deviation from the colleges that we have over there. So one more time, the z-score for the Berkeley SAT score would be 1176 minus 1263, and then divide that by 62 point whatever you got there, 67, and that will give you a z-score. So you can go through and you can compute all those values. You'll have to do the values for UNC and UCLA. You've got some values here that I've already done for you. You can just check that. But I need that in order to get in here and do the Euclidean distance for Berkeley and Caltech. And again, something else that it's explained in the book, but let me explain this formula that you're using here. It's shown very nicely on page 359 how you compute the Euclidean distance. And basically, it's the distance formula, if you remember this from algebra, only it involves, let's see, 5 variables instead of 2. So if you look at the value that I'm computing here in cell L34, this is the Euclidean distance for Berkeley and Caltech. And again, just showing you what's in what's in the textbook here in terms of the syntax, the square root, and then you have in parentheses sum of x minus y squared. So in this case, our x minus y will be the values of K26 through O26, which is the Berkeley data. And then if you put a comma, then you can go scroll in the Caltech data, which is K27 through O27. You hit a couple parentheses at the end to close this up, and you hit enter, and then you'll have the Euclidean distance for Berkeley and Caltech. So obviously, if I went down here and I computed the same Euclidean distance for Caltech and Berkeley, it'd be the same thing. So notice along the diagonals, I've put the zeros. So what you'll have to do is you'll have to go compute 6 values, this one, and then 5 others here that I show in yellow. And then you can make your assessment of how similar these two, or as you consider the pairs here, you can consider how similar these schools are. And again, just think about as you look at these values, some will be a little bit larger than the others, and then you'll decide how you determine which of these schools maybe have a little bit more in common than the other. So that should get you well down the road on problem 1. Problem 2, quick one here. So this is discriminant analysis, and we're going to use linear regression to do this. There is a bunch of homeowner data here. Homeowner data effectively looking for credit worthiness, and so there's some historical data. This set of variables, let me actually just mark these as green, and this value over here as something in blue. So apparently at some point there was a regression model that was done, and it was found that a discriminant score based on this data was developed. And this historical data has been provided to you to classify 6 individuals or 6 couples that are now applying for credit. And so 2 things we're going to have to do here. And these are based on the 2 questions here. The first thing is we're going to go through and we'll classify these records down here, these 6, based on this data, and we'll come up with a discriminant score. And then using, the historical data, and this is again expressed in the textbook. If you look at the averages of the approve and reject based on the discriminant scores, and you take the average of that, the cutoff value that we're going to use for classifying approve or disapprove is going to be about 0.49. So the first thing we're going to have to do here, and notice in the question that I asked, notice here we're only going to use 2 variables. We're going to use credit score and years of credit history. The reason being, if you went through and you created a multiple regression model with all this data, you would find that many of the variables are not significant. And so we're only going to use credit score and years of credit history. So let's do that to get started here. So if we go data analysis, this is something that we've already done before, so this is nothing new. Regression, okay. The dependent variable here will be the discriminant score. we'll use that. And then let's see, the independent variables we're going to use, just as a reminder, is credit score and years of credit history. And thankfully, we have those two right in adjacent columns, so that works pretty well. And let's see here, we do have labels. Let me see, I got to move this thing out of the way here. I don't know if y'all see that. We do have, sorry about that. We do have labels. And let's see, we'll put the output range. We want that on this page. So let's see, we'll put it, we'll put this data right here, should be fine. And we will click OK. And so here is the regression data that we're going to use to develop our scoring for each one of these new homeowner, or new, I should say, candidates for credit. Just very quickly, how does this work from here? So notice that you only have, again, one more time, we're only using credit score and years of credit history to develop a discriminant score. And this will be very simple from a regression standpoint, exactly what we've done before. So if I look at this first case where I have this data, the discriminant score will be, using the regression model as an estimate, it'll be the intercept plus the credit score coefficient times the actual credit score, and then plus the years of credit history times the years of credit history, and then I will hit return. And notice I have a discriminant score of about 0.55, and notice that actually we can actually go in here and do something really neat, I think. Let's say, we'll say if this value is greater than this value, comma, we'll put, and I think I need to put this in parentheses, we'll want an approve here. Otherwise, we'll want disapprove. Hopefully I can do this on the fly. Let's see, I might have made a typo here. Actually, I didn't. It's all good. So we would get an approve here, and then let's see, if for now, if you pull those all down, the logic assumes that you have a value of 0 here. So since 0 is less than 0.49, for now it's disapproving all these other cases. So a little fancy, a little razzle dazzle here to save you from going through that decision, and it's just something else, just one of those neat things you can do in Excel with some logic. So one more time here, just to make sure that everybody's clear. Once you finish up and compute all the regression results, it'll just be the intercept plus the credit score coefficient times the credit score from the record, and then plus the coefficient from the years of credit history times the actual credit history. And that way you can come up with a discriminant score for this case, and then you can make your decision. Just one thing I mentioned here, if we had developed a regression model to do this using all the variables, the model, many of the independent variables are not significant. So we don't want to use insignificant variables in doing any sort of estimating. So we're going to limit this just to credit score and years of credit history. And note in both cases, these are p-values are very, very small. That's 10 to the minus 12 and 10 to the minus 5. You can also go back here and look at the test statistics and see, given that they are larger than about 3, we have no problem with using this model. So this should be pretty good. So I'm approaching about almost 14 and a half minutes here. So I'm going to cut this one short, and I will get started on problem 3 from chapter 10 in the start of the next video. So I hope this helps, and we'll see you in the next video.